Okay, welcome everybody to tonight's webinar on probability and statistics. My name is Peter Fox and I'll be your host and also a panelist for this evening. And joining me tonight is Joanna, and Joanna is from Mont St Angelo Mercy College in Sydney. She's been teaching for 13 years, including Extension 2 Mathematics and the International Baccalaureate, which is how I met up with Joanna, because we were doing some IB work together. She's also produced an iBook, which people can download from iTunes. She's done some amazing videos on how to use TI-Nspire, and in 2017 was awarded Most Outstanding Supervising Teacher from, I presume that's University of New South Wales. So I'm going to see if I can get Joanna on board. Let's just see. Are you there, Joanna?
Yep, I'm here.
Okay, welcome to this evening's webinar.
Hi.
We're going to kick off with some probability, and this one in particular comes from the New South Wales curriculum documents, and I thought it was a lovely opportunity to bring in some TV. For those of you that joined early, you may have also noticed I had a multimedia view go, which was Jimmy Fallon and Mr. Cooper playing a game of egg Russian roulette. Now, if you've never played that before, and I haven't played it personally, but I have watched the video a few times because I find it particularly amusing, and I've given the activity to students to, let's just say, work out the probabilities. They have 12 eggs, 8 of which are raw, and 8 which are hard-boiled, and 4 are raw. They take turns to smash the eggs on their head, and the first person to smash 2 raw eggs loses. And in this particular game, if you didn't get to see it, it's worthwhile just Googling because it's pretty funny. They do get down pretty close to the end before they get to smash the eggs. And there's so many different questions you can be asking the students, such as, what is the probability of Jimmy smashing a raw egg, or Mr. Cooper smashing a raw egg on his head at this particular point in time, given what we already know about the eggs that have already gone by. A more challenging question is to ask students, is it better to go first or second in that game? So the host gives it to Bradley Cooper at the start to go first. And the question is, well, is that the tactical advantage? Who knows? Anyway, this one, the wall, this one is on the New South Wales curriculum documentation, but for those of you that do not read that, I thought I'd share it with everyone. And if you've never watched the show, and I've only watched part of it once to get a general idea because I saw it advertised and I thought, man, that looks like a probability game, and it kind of is. So balls roll from the top of the screen down to the bottom, and they fall in, a bit like the old clown thing, but they've got to go through a huge array of dots beforehand, or barriers, and they'll land in one of the values down the bottom. Now, it's more than just that. There's different levels to the game. They've got to answer questions, and there's balls that will knock values out and balls that will include them. You can read all the instructions. It's available on the web. You can just Google game show, wall, instructions, and get all the information. Once you get into the whole game, it's actually quite complicated. So we need to simplify it to start off with. So I've made a huge simplification to start off with and considered just one ball dropping over just a couple of levels, not the entire game board that you saw a moment ago. So the first time the ball moves, it could go to the left or it could go to the right. And there's only one way to get to each of those spaces. Now, once we get down to the second row, it could go all the way off to the left, and there's only one way that the ball is going to reach that point, because the ball doesn't seem to rebound up or jump. Once it lands, it tends to fall just between the two spots. So we're going to assume, for simplicity, it will never jump across two spots in a particular row. It will always fall to the ones either side of its barrier, if that makes sense. So to get to that location, there are two options. It could have gone from the left or it could have come in from the right. And for those of you that have seen this sort of table before, I'm guessing you've already figured out what we're going to see by the time we get down to the third row, again, the ball could have landed there by only one path, and in the next case, it could have come straight down the left, it could have taken a small deviation, and in fact there's three ways to get to that particular spot. And by symmetry we'll see obviously that this also has three options to get there. So we're kind of seeing Pascal's triangle. Now, the next thing we need to do is assign some probabilities. If we assume that the ball is just as likely to go to the left as it is to the right, then let's have a look at the probabilities. So to go off to the left, my notation there says the probability that I go to row 1, position number 1, is 1/2. It's 50-50 to go off to the left, and it's 50-50 to go off to row 1, position 2. To get to row 2, position 1, it's 1/2 squared. Now, I haven't put all the calculations in there. People can do that for themselves. And of course, to get to row 2, position 2, we see the 2C1 at the start because there's two ways we can get there. I put in the 1/2 times 1/2. I didn't put in the powers of 1. I left that out. And of course, off to the right. And it's the third row where we start to get interesting because we've got 1/2 cubed. And then to get to row 3, position 2, we've got 3C1. Now we could call them position 0 and position 1. That would give the students perhaps more of an idea on this 3C1, 3C2 and so on. So we can see from this diagram essentially what we're going to get is the binomial distribution. But the wall itself has some complications. I'll go back to that first screen later on and you'll see the complications that come into it. So I think if you're going to do this with students, the first thing you'll need to do is keep it really simple. So I'm calling this the simple wall. Now, according to Wikipedia, the 15 values, I think they are, down the bottom in the first game have the values you can see at the bottom of your screen. So we can ask the students some questions such as, what's the probability that the ball will land here? And thinking about what would be the expected return if it lands there. What about if it lands over here? It's actually got a higher probability of landing in that spot, and the value that it returns is actually pretty high. Now, of course, the way that the game is played at the start is that some coloured balls add value to your bank account, other ones subtract it. So when you've got a ball going down that's going to subtract it, you don't particularly want it to land in that location. Another question we could ask is, what would be the expected return for the entire wall? So in other words, assuming we're going to add values at some point, what would be the expected return for all of it? We'll have a look at that in just a moment. What I'm going to do is show you a simulation of this. So I've got this TI-Nspire file that I've created. Now this one is created for teacher software. In other words, it's not designed to be sitting on a student's calculator. Now this particular one, this is called the Galton board, and you can buy these where they've got little ball bearings and they fall down and create distributions, but I thought, well, you don't need to buy one. We can simulate it with this software. So what I've done, you can see I've already simulated 314 trials, and each time I click it generates another simulation, and you can see the path of the ball. And as we put more simulations in, the graph down the bottom responds accordingly. You can reset it at any time, set it back to 0. You can right click on the actual simulate button and just hit animate, and that will simulate multiple trials. We're up to 317. I don't think I need to generate any more than that. We can see that there's some sort of a distribution coming up down the bottom. The nature of that distribution, hopefully students will start to realize, is binomial. And on the next slide, we can sort of replicate that. So I've got two values at the top. I've got an n for the number of places where the ball can land. but also a P for the probability that it goes any particular way. So we could bias our Galton board, unlike the genuine thing which cannot be biased. Let's just have a look what happens if I bias the board just a little bit. So you can see we get a slight skewing. Not surprisingly, we can skew the graph off to the left, because if the probability of going to the left, let's say, is slightly higher than the probability of going off to the right, we'd expect more balls to land on the left, and so on. And we can have more or less balls in our simulation. Or if we're talking specifically about a binomial distribution, we're just talking about the number of trials and the probability of success, probability of failure, and so on. To go back to that previous problem, which I just briefly mentioned, which was coming up with the expected value for that, the wall, the simple wall, what I've done in here is I've put those prize values, or the amounts that they had stored down the bottom, I've got all them thrown in here. And you can see that I can actually just multiply the probability by the amounts. Now let me just return that to here. And therefore I can find the product of these two things. And there I have there the sum of the probability multiplied by the amounts, and we get the expected return for the entire board as $8,580. But as I said before, they have some positive values going in, some balls that are green, I think, add to the value, and the balls that are red subtract from it. Just to add to the interest, if people want to go on and study a bit more about this actual board, the game show on TV, the complications come in because we can change the location of the starting ball. So it could be dropped in at location 1, it could be dropped in at location 2, so they have 7 different spots from which you can drop the ball. And then on here, we can just simulate a ball drop and see the path that it follows. Now, I mentioned before that it gets more complicated than what we'd like it to be. So right here, we don't seem to have too much of a problem. That's just highlighting where it's landing. But the question is, what happens if I'm all the way over here at location 7? Now, it's pretty rare, and I probably won't get one while I'm just clicking away here, but you can see that potentially, there's one that got pretty close. You can see from that particular simulation that it would have been possible for the ball to end up and hit the wall and rebound back in. There's some extra maths that the kids have to do. That's what makes that particular question that they've put in the New South Wales curriculum particularly challenging, because students are going to have to consider, okay, is it reasonable to have, or are the probabilities of the locations at the top, are they evenly distributed? And therefore, what do I do about the ones where, after I get past that central location where they can hit the wall, the edge of the wall rather, and bounce back into play, because there's only 15 buckets down the bottom which capture the ball. If they go outside that 15, it rebounds back in and lands back in. Is it sufficient to say that I can simply reflect those probabilities back in towards the middle and add them back in? Does that work? So that's the game show, The Wall. So we've done one TV show, which was Jimmy Fallon. I find that one particularly funny. There's The Wall, and that's sure to engage some students because there have been some pretty good shows, or pretty high values rather, coming back in that one. And it's good to talk about the strategies that students might have. My next one up for revision is something called Calculator Blackjack. Now this one's a bit of fun because it's based on the regular game of Blackjack, with one very important difference other than it's being played on a calculator. In the regular game of Blackjack, we keep on drawing cards until the score exceeds 21. If you exceed 21, you're bust, you're out. Now, we're not getting bets on this one. All we're doing is looking at on average, how many cards, or in this case, how many random numbers do you expect to generate until you go bust? Well, in calculator Blackjack, that amounts to generating a random number, and our random numbers vary between 0 and 1. Now, it takes a while to get to 21, so what we do is we say, all right, you're bust if you exceed 1. So you can't go bust on the first round because all the numbers are less than 1 when you generate them. But I can simply say plus and generate another random number. And in this case, you can see my second random number must have been pretty small, about 0.04 something. So I'm still in. So that's 2 numbers that I've generated. So we'll generate another one. So I'm bust after 3 goes. We'll play another game. And you notice I can just arrow up and press enter. If students are doing this on a scientific calculator, you can just keep on pressing random and add the previous value. Most calculators can go up and grab the previous result. So I just have to press plus. And I'm bust after 2. People can send in through the chat space how many turns, on average, how many random numbers will I need to generate before I go bust. I had one case where I got to 3, one case where I got to 2, so we could say, well, on average it's 2.5, but long term, how many? Now, we can have students play lots of games, but on the calculator, of course, we can also simulate it. This is just a simple program that I put together on this file where it says, what sample size would you like to do? How many games, in other words, would you like to play? Well, let's play 25 games. And it says the sample size was 25 and the mean of all of those games was 2.6. Well, I can do it again. Sample size 25. This time I've got a different mean. So it must be that the mean varies from sample to sample. So let's try it again. We'll do another sample of 25. This time I've got 2.76. So I'm sort of getting the feeling that it's somewhere between 2.6 and 3.04, but it's possible I could generate another sample and give me a completely different mean. Now, another one of 2.76. We'll try another one. 2.48. So I'm getting a sense of where these numbers might be, but my mean is changing. In actual fact, if I took lots of samples, I could see how those means are distributed, and that's our sampling distribution. So wait, there's more. Here it is. If I play the game this time, calculator Blackjack, you'll see that's slightly different program name, and we'll have a sample size of 25, exactly the same as what we did before, but this time it says, well, how many samples, how many lots of these games do you want to play? Let's go for 200. Now, this is a computerized version of the calculator, so it'll run a little bit faster. But we can get a sense of what the average is just by observing those numbers populating on the screen. It's going a lot faster on my screen than what it is on yours. So we can see that the average of that sampling distribution is 2.73. So that's not for one game. It's not for 100 games. It says, I will plot the results of these 200 samples that you took, each one consisting of 25 games. So to give us an idea on what that looks like, there it is there. That's the distribution of the sample means. Now, if you don't have this software, then you can still play this game. You can have students play 25 games using their scientific calculator, give them a sticky dot, put a chart out on the whiteboard at the front of the classroom, and get them to come out and put a sticky dot where their average is, go back and play another 25 games, go back and play another 25 games, and so on. I think this is a lot quicker. So let's try something slightly different. Now, at the moment, all those samples have been recorded in a big long list. I'm going to say SAMP25. So what I'm doing is just making a record of all of those samples. I've now got a backup of it, something that I called SAMP25. And now I'm going to play the game again. And this time I'm going to take a sample size of 100, 4 times the size that I had before. So in other words, I'm going to play 100 games, and I'm going to play that 200 times. So this will be a little bit slower. I should have some background music while this is going. But the first thing students may notice is that the sample average is not jumping around quite as much as what it was before. Well, that's because I'm playing 100 games and taking an average. So I don't expect it to jump around as much as what it did before. If you were watching before, you may have noticed the sampling distribution, the standard deviation of it, but let's just have a look at what the spread of that data looks like. We can see it's much more compacted. In actual fact, I can now add back in my sample where we had 25 games in each one, and see that its distribution is further spread out than what it is if we play 100 games and calculate the mean each time. Let's have a look at this value here, 0.088. That's the amount of spread, the standard deviation of this particular one. Let's compare it to the standard deviation of the previous one, 0.16. 0.16 compared to 0.08. In fact, the sampling standard deviation of my sampling distribution is approximately half of what it was before. And for those of you that already know the mathematics, it says that for a sampling distribution, its standard deviation will be sigma on root n. So because I've made it 4 times the size that it was before, then my sampling standard deviation, for my sampling distribution is actually half the size. It's come out exactly what is predicted. What I think is particularly cool for this activity and why it's one of my favorites is the average is 2.713. If I was to do more or take larger samples, we would find it would tend towards 2.718, or in other words, E. And I think that's pretty cool, that a simple game like this produces a theoretical mean of E. And how can we be more certain about that? Well, we could do all of the calculus along to calculate it, or we could just increase the sample size, not the number of samples, and that's important for students to understand. I would increase the sample size, and that would give me a smaller deviation. I would be more certain about the result. So I've taken up the first half of this webinar. Joanna's been waiting there patiently in the background, ready to present some information on statistics. So I'm going to transfer the presentation across to Joanna. Are you there, Joanna?
Yes, thank you very much, Peter.
You're welcome.
That was really good. I like your simulations. Very nice. Okay.
Now, there's Joanna's screen. That was quick.
Yes, great.
Very good.
Yes.
It's all yours.
Wonderful. Thank you. Okay, so I'm going to go over some statistics in the TI-Nspire to cover some of the New South Wales new curriculum outcomes and show how you might like to explain it using the TI-Nspire software. Okay, so for my first file, it's just called Outliers, and we're going to look at the following outcomes. So we've got S1.2 discrete probability distributions, so evaluate standard deviation and variance of data sets, understand the sample mean, is a better estimate of the population standard, sorry, I thought you'd say standard deviation, is a better estimate for the population standard deviation as the number of data values increase. And we're also going to look at data and summary statistics, so investigate the effect of outliers on the mean, median, and standard deviation. Now, within this file, the second sheet are some instructions that you might like to follow when doing other examples. So on page 1.3, we've got a spreadsheet where we're going to put in our scores. And you can see right here, we've got a nice dot plot to see, to actually see the scores, a graph of the scores. Okay, Now, I've also got a Word document that has some questions that you could do with your class to demonstrate, how to find statistics, how standard deviation works, how outliers affect the statistics. So I'm actually going to skip question 1 and go to question 2 because it's a lot of data here and I've already entered it for you. So with question 2, it says 50 students were asked how many siblings they had. The data for the population is shown below. Okay, so the first step is enter all the data in column A of the spreadsheet on page 1.3. Luckily, I've actually done all that for you and you can see the dot plot there. Now we're going to write down the population standard deviation shown in column E. So if you just press across, scroll across, and I've created this column so that you can see the population standard deviation right here. For this data is 2.18. So let's write that down there so we can remember it. Okay, now we're going to delete all those values and into the first row of values as a sample of our population. So let's go back. And if I just click here and kind of drag it down, okay, and then I'm just going to say delete cells. Okay, now we're just going to enter one row at a time, and hopefully what we're going to see as our sample increases, our sample standard deviation is going to approach the original population standard deviation. So I'm just going to enter the first row. So it was 1, 3, 5, 2, 4, 3, 10, 2, 0, 2. Okay, now if we go across, and so as you can see, our little graph has changed, and we've just got a little bit of data now. So now if I go across again, I can see my sample standard deviation is 2.78. So let's write that down over here. So let's write down the sample standard deviation, 2.78. We're quite a bit bigger than our original standard deviation, so let's keep entering data and see what happens. So my next instruction is at the next row of the data. Okay, so now I'm just going to enter the next row, 1, 0, 2, 3, 2, 1, 7, 0, 2, 1. Okay, what's good about this, we're entering it manually, which might seem a little slow, but it's just driving home to the students exactly what we're doing. We're increasing our sample size, and then we're seeing the effect on the standard deviation. So now sample standard deviation is 2.45, which is closer to our original standard deviation. And so let's just do one more roll now, and hopefully we'll see continue to approach it. So the third row, 4, 1, 1, 1, 8, 3, 1, 2, 1, 1. Okay. Okay, and now our sample standard deviation is 2.35. So as we can see, the more data we add in our sample, the closer we get to our original population standard deviation. So that's just a simple way of demonstrating that fact to students. So you can repeat this now, add the next 2 rows, and continue to see the standard deviation approach our original. But I think that's enough for now. So now let's go back up to question 1. So basically, this is just a simple question to just enter some data, whatever that is, and then you can easily see the mean, median, population standard deviation, and variance. So you can enter any of these lists, and you'll see it all in column E. So for our data that we've got at the moment, which is all this, you can see the values there. So for this data, the mean is 2.46, the median is 2, the population standard deviation is 2.31, and the variance is 5.38. And you can do that again with any of these lists here. I won't repeat it because basically we've done it already for this. But so that's a way to show how that works. Now, actually, no, sorry, I will do it for A because I want to show you what happens with outliers. So let's just clear that data. Delete cells. And I'll enter the data. So it was 24364. Five 524 311. Okay, so here's a small amount of data, and here's our mean 3.33, median 3.5, standard deviation 1.54, and variance. Now, the other thing we want to know is what happens when we have outliers. For instance, I can now come onto this graph and drag this away from the group. Okay? What do we notice? As I move this around, what doesn't change? The median. Because the score that's the median, it doesn't matter where this first score is, it just matters that it's down the bottom. So the median, because it's a position, it doesn't change. Well, it depends on position as opposed to an average. But we do see the mean changes. So as we decrease the score, the mean drops. As we decrease the score as well, the population standard deviation increases because we're more spread out. And similarly, the variance increases. And you can do that on either side. So if you wanted, you could drag this one higher and higher and higher. And look at that, it's now, it's saying 8.1, but it's showing there. So what I could do to see what I've just done is change the window. So if I go menu, window zoom, window settings, if I want my X max to be, say, 10 and my X min to be 0, now I can see this outlier a little bit better. So I can drag this around, make my outlier a little bit more obvious. And so we can see how the statistics change, which is very nice. So it's a little bit more visual way of understanding why statistics change for outliers. Okay. So now we're going to look at a file I've called box plots and show how to show box plots for a data set and parallel box plots, which is in the curriculum. So for this is the outcome: organize, interpret, and display data into appropriate tabular and/or graphical representations, such as parallel box plots. So if you've got some data, so here's the instructions here, sorry, but I'll talk you through them. So here's our data. We've got, say, class 1 and class 2. And here are the corresponding box plots. And it gives a great visual representation. It shows how this median, and all you have to do is gently drag the cursor around, and you can see the statistics come up. So the minimum, quartile 1, quartile 2, or median, quartile 3, and upper extreme or maximum value. So let's go to the question. Question 3, which you could do with your class, 2 classes of 15 students, set the same test, and got the following scores out of 20. Enter the data for class 1 in column A of the spreadsheet on page 1.3. So for class A, I believe it's actually already in there. So it's 8, 12, 15, 13, 14, 17, 20, 13, 18, 18. So, yep. And 14. So there's all the data. Now I think there's a typo. That should not be 114. Doesn't make sense. That's just 14. So, and then class 2, you you can put in your second column, which is all there. So, and you can do that with like 2 other sets of data and just put in those 2 columns, call them whatever you want. And then here's our corresponding box plots. So it's a nice, easy way for a student maybe to see them for the first time and read them. So the question now says, write down the 5-point summary for each class. So we can easily see class 1 is blue. So the minimum value is 8. Quartile 1 is 13, and the median is 16. The upper quartile is 18, and the maximum value is 20. Now, class 2, we can see it all here. The minimum value was 3. The quartile 1 is 12. The median is 15. The upper quartile is 18. And then the highest amount was 19. Now, write down the range for each class. So that'll be for class 1. That'll be 20 minus 8, which is 12. For class 2, sorry, that'll be 19 minus 3, which is 16. So now it's about interpreting it. So which class do you think did better on the test and justify your answer? So by looking at the spreadsheet, students, you can brainstorm with students. Hopefully they'll notice that the median for class 1 is higher than the median for class 2. The range is clearly smaller, which we also found by calculating it. And also the interquartile range is smaller. And also the highest value is also bigger and the lowest value is bigger. So for all of these reasons, hopefully they can easily see that class 1 overall did better on the test. Okay, so that's box plots. Now my last file, bivariate data analysis. Okay, so we're going to construct a bivariate scatter plot to identify patterns as well as direction and strength of the association between the 2 variables. We're going to calculate Pearson's correlation coefficient, R, using technology, obviously, and quantify the strength of the association. And we're going to fit a least squares regression line using technology and interpret the gradient at y-intercepts and make predictions using interpolation and extrapolation. So we're going to do all that, use all these outcomes for the New South Wales syllabus using this file here. So in 1.2, I've got some more instructions how to use this file. So 1.3 is our spreadsheet where we're going to enter our data. Now first I've got one example that corresponds to question 5 here. So where you can enter your data. Now it's best to do the independent variable in A, dependent variable in column B. So I've called it height and weight. So for all these height, there's a corresponding weight. Entered them in. And so write down the correlation coefficients. So if you scroll across and down, the correlation coefficient is R, which is in this case 0.90756. So it's up to you how you want to round it, 0.90756. Okay, what does this value mean for the relationship of the variables? So the fact that this value is positive and it's quite close to 1 means that it's got a very strong positive correlation. Or in other words, as height increases, according to this data, weight also increases. Okay, and now write down the equation of the regression line. Now, we'll just use y and x since I haven't given any other variables. So it would be y equals, now our regression form is, it's telling you here, it's of the form y equals mx plus b, where m is 0.5852 and B is negative 37.3447. So the equation would be y equals .5852 x minus 37.3. Okay, now we can actually see this as well. If we go across to 1.4, here's our scatter plot with all our data values, and here is our equation line, equation of our regression line already. Now this here is R squared, not R. The New South Wales syllabus is more focused on R. So that's a really nice visual interpretation, which is good. And as we can see, here's a line that goes through it, which is excellent. Now, what we can do, use this equation to predict the weight for someone with a height of 164 centimeters. Now, what we can do is just sub it in and use a calculator, but let's use the technology to actually trace the graph. So if I go menu, actions, analyze, graph trace, and a point pops up at 159 and 55.7. So let's move across now and try and get as close to 167 as possible, which is about here. So there's 167, was it? No, 164, apologize. So let's go back. Okay, so it's about here, 164. And as we can see, approximately, this will be about 58.7 kilograms. And this is interpolation. This is because this value of 164 is within our data points. It's between our data points, like the x values and y values of our data points, which makes it a more predictable prediction. Reliable prediction, I should say. And now if we do an extrapolation example, use this equation to predict that weight for someone with a height of 180. So now if I go across a bit more, 180, keep going, keep going, keep going. I'm just pressing across to the right. There's about 180 all the way up here. And that corresponds to approximately 68 kilos. But because it's outside our interval of data, with our range of data, it's less likely to be accurate. A good way to show the inaccuracy of extrapolation is if I go the other direction. Just keep going, keep going. Now look at this. As we get shorter and shorter, our weight goes down. If I keep going, what does this say? Now look at this. So a baby or someone that's 63 centimeters in length apparently has a negative weight, and it keeps going in the negative direction. So this is a nice way to show that extrapolation, when we go outside the data, not so reliable. So that's a nice extreme way to show that. Now, if we go back to previous example, so let's have a go at this from scratch using the same file. So 10 students were asked how many absences they had during the term and what they got in the end of term quiz grade. Now, the results are shown in the table below. Enter the data in the spreadsheet. So let's go back now, and I might rename these variables. So it's got absences and grade. So if I call this absences and grade, and now I'm going to enter my data. So it goes 1, 1, 2, 3, 4. Yeah, it's going to be annoying, isn't it? All right. It's not liking the fact that I have different number of data in the column, so I'm just going to delete these. to make life a little bit easier. Okay, so it goes 1, 1, 2, 3, 4. Seven, 8, 9, 10. Okay, I'm going to start from the bottom this time, and then going back up, it's 50, 60, 63. Okay, 65, 80. 88, 88. 95. Oops. All right, so here's our absences, here's our grade. Let's go across. Okay, what is this happening? What's happening here? Okay, the gradient is now negative 4.91, and the y-intercept is 101. So if we look now, what's going on? I can't see my data. That's because my variables are weight and height. I don't want them to be that anymore. I want them to be absences and grade. So let's click on this and choose absences. And now let's click on this and choose grade. And there's our lovely data and our linear regression line. Now, as we can see clearly, there's a negative relationship which corresponds to our correlation coefficient of negative 0.9899. So if we go back to our question, the correlation coefficient, which is a little r, is negative 0.9899. Okay, what does this value mean for the relationship of the variable? Well, they have a very strong negative correlation, because it's very close to -1, which also means, in other words, as the number of absences increase, generally their quiz grade decreases because they're learning less content. Write down the equation of the regression line, so that's using this, y equals negative 4.91x plus 101.1. Now, use this equation to predict the quiz grade for someone with 5 absences. So that's interpolation. So again, they could just substitute 5 into the equation, but let's try and use the line. So if I go menu, analyze, graph trace, and, oh, you didn't like that. Okay, so let's, okay. So now here it is. So if I just move my cursor over the line, it came up. So let's get as close to 5 as possible. Okay, so predicting it's approximately 76. So if they have 5 absences, they get approximately 76 grade. And again, that's interpolation because we're within the data. We're in between data values that we were given. Now we're going to predict the quiz grade for someone with 15 absences. So let's just keep going across. Okay. So that's close to 15 absences. Oops, sorry. So we're getting approximately a grade of 27, which is quite low out of 100. And now, someone with 0 absences, okay? Let's go all the way back to 0. Oops. All right, as close to 0 as I can get. We've got 101. We're getting about 101 when we're really close to 0, which corresponds with the y-intercept of 101.1. That means for someone that's always present, they're getting 101 out of 100. Doesn't make a whole lot of sense. Again, showing the unreliability of extrapolation, not as reliable as interpolation. So the answer to that one is 101. So that's also signifying the meaning of the gradient and y-intercept. So the y-intercept is what happens when you're, in this case, in this example, it's for someone with 0 absences, the grade they would get. The gradient is how much the grade drops by every time someone, every time someone is absent. So now something else we can do, if I just click on the line and I want to actually edit this point, so I can double click on the point, or I can click right click. Sorry, there's too much going on. I'll just move something. There we go. I'm trying to double click in there, but it doesn't seem to want to, so I won't worry about it. But you can investigate exactly by subbing into the equation. If you see what it is for 0 and then 1 and then 2, you'll see we're going down by the gradient. And that's the meaning of the gradient. It's how much it's dropping by for every absence. Okay, so that's it from me.
Just before you leave that one, Joanna, there was a question from one of our participants to say, can you view the residual squares? So we've, I assume you know how to do that one before, but if not, under the menu.
Menu?
Yep. Then we can use Analyze.
Residuals?
And Residuals, and show residual squares.
And there we go.
So for students, it's a lovely visual to show that we're working out effectively the sum of all of those squares, and when the sum of all of those squares is the smallest number as possible, then that is our line of best fit. The other one that's particularly useful, because just because the R value is, let's say, close-ish to 1, then we can still have perhaps a better line. So this one suggests that it's probably linear, just looking at the data, but change your residual view to residual plot, because we want to look to see if there's a pattern in the residual plot.
Right, so how do I do that?
So residuals, analyze, analyze residuals and residual plot.
Show residual plot, yep. Okay.
And it splits the screen into 2, so we can see that our scatter plot is still located up the top. And as those points effectively fall randomly above that 0, it's saying that there's no pattern. But let's suppose they form some sort of pattern, like the end ones were above and the middle ones were below, which is a common example. Then that would suggest that there's a pattern in the deviation from our line of best fit, in which case it might be a better model if we had a different curve rather than a straight line. So that's a great tool that people can see it. But just the residual plot, just the residual squares, is a great visual for students to understand what it means to be as a least squares revision line of best fit there.
Excellent, thank you.
And that was all from you, I understand?
That's it from me, yes.
All right, so let me just transfer the presentation back to me. Now, I had one last thing I'd like to share before we finish off for the day. Just wait for my screen to come back up. What I've got here, and I've only got about 2 minutes to show it, but that's about all I'll need, is a general bell-shaped curve. Now, you'll see that the area under this particular curve does not equal 1. Now, what does the equation look like? The equation says it's ae to the power of negative b x minus c all squared. So what? Well, we've got some dilation factors in there if we're thinking about functions, a and b, and c looks like it's some sort of a translation. So let's explore. I can go back to my graph and I'll change the value of a, and we see as expected we get a dilation which is parallel to the y-axis, and that's causing the area to change. I can change the value of b and get a dilation parallel to the x-axis, and you'll see the curve becomes a little bit narrower. And in fact, if I explore a little more, I could get that area to be approximately 1, in which case I could claim this to be some sort of a probability distribution, or at least it could be, because the area under the curve is equal to 1. So let's explore this translation. And we see that that horizontal translation doesn't make any difference to the area under the curve or the area bounded by that curve. And I'm going between negative infinity and positive infinity, as you will see by the integration there. It's not exactly 1, it's 1.002, so I won't claim it to be a perfect distribution. But there is a perfect distribution where that area is always equal to precisely 1, and that is referred to as the normal distribution, that bell-shaped curve. And once we've introduced students to that regular sort of bell-shaped curve, that is the one that I had up on the screen before, and see that there's a horizontal and, a parallel, I'll try that again, a dilation parallel to the x-axis and y-axis, then have a look at the actual equation for the normal distribution, and students should see that the standard deviation, which is what causes a spread, is in the formula in both the locations where A and B was found before. So, the really cool thing about the normal distribution then is that I can change its shape. And you'll see that we're getting that dilation parallel to the x-axis and the y-axis at the same time, whilst maintaining a total area under the curve equal to 1. And if I change the mean, I've left a little shadow behind, and that therefore, if that area is equal to 1, and this curve is still symmetrical, then these values for which I'm calculating the area between, that is between A and B, and they can be a little bit troublesome to grab a hold of. Let's see if I can grab a hold of him. He's going to be a bit recalcitrant while I'm holding the phone at the same time. So the graph down the bottom is our standard normal distribution. The one at the top is our current distribution, that is, in this case, has a mean of 4. Let's give it a really simple standard deviation of 0.5. So what we're saying is that the graph on the top is just a morph of the graph below, and that if I change the values of A and B, they must correspond to some points on the graph below as well. And it's not going to let me change them either. It says I've selected more than one thing. No, it's being annoying. Never mind. We can see that the translation of those points and the corresponding dilation of those points is written below as ZA equals XA minus mu over sigma. So its corresponding spot on the standard normal is negative 1.5, and for the value of B is 1. How that makes sense is because A is lower than the mean and B is above the mean, so we can see that in their standard normal values. The one that is below the mean, that is A, is negative, and the one that is above the mean is positive. And looking at the time, that's about it for this evening. Hopefully participants have got something out of tonight's webinar, and at the end of the webinar you should, let me just get that presentation running, you should get an email for a certificate. We'd also appreciate your feedback. If you've enjoyed some of the things that we've presented tonight, by all means say so. If you had any difficulties, let us know, or if you're wanting some more information about the sorts of things that we can do with Inspire, by all means include it in that feedback. Some people actually say, can you do a webinar on this particular topic, like how do you make those really cool animations? And you'll get a link to the actual video so you can watch it on demand. And in fact, all of our videos are on demand, and we also have some student exam videos, particularly useful at this time of year so that they can prepare for examinations. There's also some questions attached to those. To keep in touch with us, subscribe to our e-newsletter so you can find out about events as they come up. If you're in Queensland, for example, we have some PD opportunities for you up there. And finally, if you have any questions, by all means, give us a call. And that's about it for us tonight. Thank you, Joanna, for your presentation.
Thank you, Peter. It was fun.
And Thanks everybody for joining us, and hopefully we'll catch you next time. Bye for now.